Hello students. In our previous lecture we understood how analog signal is converted into digital signal, and we also seen the importance of 0 and 1 means a binary representation, and how robust and error resilient system would be a binary system. Now we would like to answer an important question in this particular lecture. The question is how to represent information in binary form. Okay, so to help to understand this particular question itself, so we have two particular sub questions. One question is, let's say, a 2-bit number. A 2-bit number can have 4 states: 0 0, 0 1, 1 1 and 1 0. So these 4 states, to which number each of these states should map. So we can say that a 2-bit number can represent 4 numbers: 0 1 2 3 4, 0 1 2 3. Now whether 0 0 should represent 0 or 0 1 should represent 0, and similarly 0 1 2 3, how these 4 numbers would be mapped to 0 0, 0 1, 1 1 and 1 0. So one thing is clear, it is going to be 1-to-1 mapping. So that means no two numbers can map to the same decimal number, or similarly no two decimal number can map to same binary number. So we have to have some sort of 1-to-1 mapping, but which mapping is most natural? And this problem will become more complex if we'll have more number of bits. Let's say we have 5 number of bits, or 10, 20, 30. If the 30 bits are there, the combinations are 2 to the power 30. So which combination will correspond to what digital number or what decimal number is the question which we would like to answer in this lecture. To answer this question, we can learn from history. Historically, each culture or every region in the world, they have developed independently. Because they have developed independently, so they developed their own language systems. That's why every part of the world has their own languages. Now, as people invented languages, they also find the need to count numbers, to count number of people, to count number of objects, etc. So that's why they invented their own number systems. And if we observe many of these number systems, most of them, they were based on some sort of a base system, or in Indian system we have typically based things onto base of 10. Okay, but at some other places, like if we want to calculate weight, so in weight we had a different system where we had different notion, like 5 kg and then 40 kg, etc. So similarly, at different places of world, in part of Europe, base system of 12 was quite common, and Spain and France like places, they had a base system of 16 as quite common. So similarly, at other places, base of 15, base of 20, so all of these were common base systems. And now how they counted large numbers? So many people, they at many places they used multiplication or position based number system. So where each number, where each position in the whole number represent the value would be different. Okay, while there were other systems where different symbols represent different values. For example, Roman numbers. In Roman numbers, I means 1 and V means 5, X means 10 and L means 50, C means 100. So they keep on inventing different symbols for different numbers. So if you want to count a very large number, then there would be a different symbol for each word. Okay, so each symbol would carry its own value. So based on this system, now we can also classify all these systems into two parts. One is position based, another is non position based. So in position based number system, like there would be fixed set of symbols. For example, in decimal, so there are fixed set of symbols. There are 10 symbols: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now based on where that particular symbol is there in the number, it will determine its value. So if it is at units place, the value is same as the symbol. But if it is at decimals, if it is at tens place, the value is multiplied by 10. If it is at hundreds place, the value is multiplied by 100. While in non-positional system like a Roman, like your value is determined by what symbol you are using. It doesn't matter where the symbol is. So let's say XXX means 30. So it doesn't matter where X would lie. So but there is also some relation between if X is before L or after L, the value would be different. Okay, so, but its X value would still be 10 in whether it is after L or before L, but overall value of the number would be different based on the position. Now, after inventing so many type of number systems across the world, finally we have converged onto position based decimal system. The reason is that using these 10 digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, we can represent any large number. You need not to define a new symbol for a large number. Whatever is the largest number of the world can be defined using only these 10 symbols. Additionally, what have been observed that, for example, Roman numbers or non-position based numbers, even any number which was of different base than 10, calculation was difficult. Like addition, subtraction, multiplication, finding square root. So all of these things were slightly difficult if we were using some other base other than 10. So that's why finally we have converged onto a position based decimal system where the base was 10 and each position carried its own value. Okay, so based on this learning from the history, we will simply use this position based system. So instead of decimal, it would be binary. So where there are only two symbols, 0 and 1. So it would be position based binary system that we'll use for our purpose. Now let's try to see theoretically, like if value depends on the symbol, as we can define it by this particular equation. So in this equation, n is equal to, let's say there are n numbers. There's n plus 1 symbols are there. The symbols are fixed. So let's say if it is we can also generically defined as R radix system. So R is the total number of symbols which are present. So let's say R are the number of symbols, and the number has n minus 1 such digits. So this number can be represented as, so addition of AI position value position at ith position into R is to power I. So this looks complicated, but let's try to understand it with the decimal system. So let's say we have 483 is a number. So now at units place we have 3, at units place we have 3, and at tens place we have 8. So 8 would be multiplied by 10 is to power 1, and 4 would be multiplied by 10 is to power 2. So radix was 10 or base was 10. So that's why each number, like as we go from left to right to left, as we go from right to left, so LSB would be multiplied, will always be units place, and from LSB if we go towards MSB, the power of base will keep on incrementing by 1. So here power of base means r is 1, here power of base means r is 2. So 10 is to power 2 is 100. So we keep on going like this. Since we have understood or we have seen this particular system since our elementary classes, we are so apt, we are so adapted to this system that it comes naturally for us to read numbers in decimal places. And that is why throughout the course we'll talk mostly about whenever we see numbers, we'll see in terms of decimal numbers only. If it is explicitly specified, it would be specified that number is represented in form of binary or some other radix. But this formula is generic, so it is applicable for any radix, any particular number. So this position based number system is not only applicable only for integers, but it can also be used for fractions. As we know, so if I want to extend this formula for fractions, then it will become let's say a minus 1, so like position number minus 1, position number minus 2 up to position number minus m. So here in this number there are n plus 1 digits before decimal point and m digit after decimal point, but the formula still remains same. So the most important thing is that at the decimal, your position here is the pivot point where you're starting counting of your radix power. So for example, here if I would like to see any number which has a sort of decimal, let's say 1.74, so 1 means units place and this is before decimal. So my LSB will start counting only at the decimal place. So if it is before decimal, then I'll start counting it like a LSB, and then I'll go towards the most significant byte. LSB means least significant byte, and MSB is most significant bit. Okay, so my powers of R will start incrementing after, like before this decimal place, and after this decimal place it will start decrementing. Here 1.74, we understand that it is 1 plus 7 by 10, so means 10 is to power minus 1, and plus 4 by 100 means 4 into 10 is to power minus 2. So in this way we can represent any kind of a number, be it a absolute number, integer, or it's a fraction. So let's try to extend this position based number system to binary system. So let us see it using this example. So when radix or base is 2, then it is a binary system. Total number of symbols which are available to us is only 2, that means 0 or 1. And as we move along to the positions, my 0th place or units place will have a power of 1. It would have multiplication factor of 1, and then first digit, first bit, so this is 0th bit, this is first bit would be multiplied with 2, and second bit would be multiplied with 4, third bit would be multiplied with 8, so that means 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6, and 2 to the power 7. So this way, as we move from least significant bit to most significant bit, power of 2 is kept on incrementing. Let's see it with an example, that let's say we have some number which is 101, 101, 101, and I want to convert this binary number to a decimal number. So what it would be, that I need to see from the least significant bit, that is 1. So 1 would be multiplied by 1, and the next bit is 0, I am ignoring that, and then at A2 place I have 1. So A2 would be multiplied by 4, and then A3 is again 1, it is multiplied by 8, and A4 is 0, A5 is multiplied by 32. So here you see, multiplication is not a multiplication, but it is actually a replacement. So if bit is 1, its value is replaced. If it is 0, it's ignored. So that way this particular number will become 32 plus 8 plus 4 plus 1. So if I add all of them, it will become 45. So this way a binary number can be represented by using the same formula, by calculating the power of or calculating the value at each place. Now if I would like to convert a number which is a fractional number, so let's take a fractional number example. So it can be extended in the same way. Here things would be like at before the decimal place, like all this the integer part would be calculated in the same way we had calculated this binary part. So here we'll start with this 1 and after that its value is 1 here. Now a1 is 0, so we are ignoring this, we are not writing it in this calculation part, and a2 is 1, a2 value is found to be 4, so 4 plus 1 we can write this is the integer part. Now what is the fractional part? Fractional part is also 101 here. So a minus 1, after decimal we have started minus 1, so minus 1 means 2 is to power minus 1, 2 is to power minus 1 is 1 by 2, 1 by 2 is 0.5. So this 1 would mean a 0.5 in decimal. Now the second place a minus 2 is 0, we can ignore that, and a minus 3 is 1. So a minus 3 is 1 by 2 is to power 3, 1 divided by 2 is to power 3, that means 1 by 8. 1 by 8 is 0.125. So if I add all of them, it will become 5.625. So this is how a fractional number can also be represented or converted to decimal if I keep following the formula which we mentioned in the previous slide. So this formula can be used generically. Okay, so now after this, so we can summarize that this binary system can be represented, and now we also know how to convert. If there is a binary number given, then how we would convert it into a decimal number. Okay, so let us see the next thing, that if a decimal number is given, how to convert into a binary number, or in general to any number with base r. So most of you know this calculations. This has been done in your higher secondary classes or in your schools. So let's revise it for the sake of completeness and for benefit of everybody. So let's say number n, which was represented in a decimal number, and we want to convert into a base r. So what we do is we divide this number n by r. Whatever is the remainder, that bit is r0, a0, and the quotient become a new n, and then we keep on calculating, again divide n, a new n by r, and then the remainder is the next bit. So the subsequent bit we can keep on generating using this. Let's see this with an example so that we can understand it better. Let us say we have this number 53, which is represented in binary, in decimal, sorry, in 53 is represented in decimal. Now we would like to convert it to a binary. Because it is binary, base is 2. So we have to divide every time this number by 2. Now initially we divided this 53 by 2, it will come out to be 26, and the remainder is 1. And because remainder is 1, so this will form the least significant bit, 1. A0 will be equal to 1. And now new number is 26. This 26 has to be divided again by 2. By after division, the new number is 13, and quotient is 0. Sorry, remainder is 0. So because remainder is 0, this will become the subsequent bit for that new number, for our binary number. Now after 13 we again divide it by 2. Quotient is 6 and remainder is 1. Because remainder is 1, this will become subsequent binary bit. And again we divide 6 by 2, it will be 3. Here a remainder is 0, so my subsequent bit, binary bit, is 0. And again I divide 2 by this, my number 3 by 2, the remainder is 1, and a remainder is 1 and quotient is also 1. So because remainder is 1, my subsequent binary bit is 1, and again I divide this 1 by 2. Here quotient is 0 and remainder is 1. Because remainder is 1, I have represented next bit as subsequent binary bit as 1. Okay, so the thing which had to be noted is that we are doing this process until we reach to the quotient equal to 0. Till the number becomes 0, we are keep on dividing this number. And the second thing to be noted is that we will receive first least significant bit, and in the end we get most significant bit. And every time we can keep on incrementing these bits. So in other words, I can rewrite this as this 53. So this is also one representation we have to remember. Whenever 53 subscript 10 is written, that means the number is represented in a decimal form, and whenever subscript 2 is given, so that means number is represented in a binary form. So in whenever we will talk in questions or in exams or in slides, by default we would be representing a number in a decimal form. So that means if there is no radix specified, that means the number is in a decimal form. If radix is specified, then that would be the representation of that number. Okay, or otherwise we will write explicitly that the following number is a binary number or following number is a decimal number. Okay, so here 53 in decimal has been written as 1. So this is the MSB 1 1 0 1 0 1 1 0 1 0 1, and this is the decimal representation. So this is how a number or an integer would be converted into a decimal number. Now binary number. So let's say if this particular number is not an integer but a fraction. So how to do it with a fraction? In fraction, the process would be difficult. Process would be little bit inverse. So first of all, let's say we have received one particular number, let's say 3.5. So we will separate, we'll make two parts of this number, one as an integer part, another as a fractional part. Integer part we will do using this process where we'll keep on dividing, and the fractional part we'll do using the process which we are going to discuss now. So in for fraction, what we'll do is we'll keep on multiplying the number, multiply with the base r, and whatever non-fractional part we generate, that will become a minus 1, and subsequent digits we keep on getting by multiplying, by repeated multiplication, and whatever is the non-fractional part will be the next subsequent digit. Again, let's see it with an example, so to make things clear. And here, because we would like to convert a decimal number into a binary number, so our base would be 2. Okay, so let's say we want to convert a 0.7, which is represented in a decimal number, to a binary number. So first thing we do is, as given in this formula, first 0.7 would be multiplied by 2. Because it is multiplied by 2, we'll get 1.4. Now what is the integer part? 1. Non-fractional part is 1 and fractional part is 0.4. So 1, we will take it as a minus 1 is 1. Now the fractional part 0.4 we take and then again multiply. This is 0.8, and 0.8 because here non-fractional part or integer part is 0, so we can say a minus 2 is 0. And we take the fractional part, which is 0.8. 0.8 would be again multiplied by 2, it becomes 1.6. And because it is 1.6, fractional part is 0.6 and integer part, non-fractional part is 1. So a minus 3 is 1. Again we take the fractional part, 0.6, 0.6 would be multiplied by 2, that become 1.2. Here fractional part is 0.2 and non-fractional part is 1, so we can say a minus 4 is 1. And this 0.2 again would be multiplied by 2, it will become 0.4. Here non-fractional part is 0 and fractional part is 0.4. So 0.4 we can take to the next row, and 0.2 again we multiply with it become 0.8. So this particular part will now represent the binary number. Now we can say that 0.7 in decimal is equal to 0.1011100 in binary. Now there is this, for this particular number there is one observation, that this number is a non-rational number. So that means these bits in binary it is non-rational, because 0.7 is not followed by 0, but this is not completed. So that means here in the multiplication we have not received 0, so that means there would be some part which is keep on repeating. So that repeating part we can observe here. You see this pattern 0.4, 0.8, 0.6, 0.2, and because we have received 0.4 again, so that means this pattern is going to be continued. So these four digits, these four binary digits 0, 1, 1, 0 will keep on repeating. So we can also say this number as 0.10110, where 0110 will keep on repeating itself to infinite. Okay, so then it would be close to then the value would be very close to 0.7. Okay, so this is how we can convert a decimal number to a binary number, be it a fractional or non-fractional number. Now one more thing which we will finish in this, which we'll try to understand in this lecture, that is there any other base, like in binary we have base of 2, is there any other base which is important for us in this particular course?